recording posted for Monday's class, by the way. I just got it posted this morning. So it is out there under external links in Blackboard. Just a reminder, things that are due tomorrow, that'll be Thursday, November 2nd. We have the PNL for M6. We're going to be covering M6 today. Then the out of class exercises for M5. That was what we covered on Monday. Those will be due tomorrow. Okay, so picking up then where we left off on Monday, I want to actually look at a couple of examples off of those out of class exercises from M5. One of them is talking about the half-life of drugs in the bloodstream. And we're actually looking at number 1 on the out of class exercises for M5. Talking about Jacob drinking coffee that contains caffeine. And he's drinking 310 milligrams of caffeine. And his body metabolizes or eliminates 13% every hour. So we want to first kind of create a model for this. And if you remember, our model was some amount, so we're just going to use big C for caffeine in the bloodstream, is equal to some initial amount, some starting amount, times a factor, and then that was to some power that was related to time or whatever our other variable was. So in this case, what is the starting amount that would go into this model? How much caffeine did Jacob consume? 310 milligrams. So we're going to put the 310 in there as the starting amount. Now there's some assumptions there. One, we're going to assume that Jacob consumed the coffee very quickly. Because if it was spread out over 20 minutes or so, that's going to change things. So we're going to assume that 310 is just instantly in the body. Now the factor, the next part, always relates to 100%. Now it depends on whether this is an increasing problem, a growth problem in other words, or if it's a decreasing problem, or a decay problem. In this case, which is it, a growth or a decay problem? We're talking about number 1 on the out of class exercises, the metabolizing caffeine in the bloodstream. It's decreasing. This is a decay problem. So if it were a growth problem, we would take 100% plus whatever percent was given. Being that it's a decay problem, we're going to take 100% and we're going to do what to it? Subtract. And what percent is given in the problem here? 13%. So what that means is at the end of every hour, 87% of the caffeine is going to be remaining in the bloodstream. That's 87% of whatever was there at the beginning of each hour. So in our model down here, it's going to be 310 times what? %, is going to become 0.87. Good. And then our variable for time, we can just put in T, and then C is caffeine. And we should always make sure we specify what our variables mean. C stands for milligrams of caffeine in the blood. T stands for time in what units? If we look in this problem, we're doing that 13% applies to, is that every minute, every day, every hour? So it's time in hours. So there's our equation. One of the things we explored last class was we explored time to double and time to half. Now, of course, in this case, being a decay problem, it can't double. So what we're going to be looking at is the time it takes to half, which is often referred to as the half-life. So the half-life of this caffeine is the length of time it takes to get to half of the amount that it started with. If you recall, we had done some examples last class where we were doubling, and it didn't matter what the starting amount was. The time it took to double that amount only depended on the percent. So in this case, all we care about really is that 0.87 to the power of t. As soon as that is as close as possible to 1/2, that is our time to get cut this in half, our half-life. So we don't really even need to worry about the 310 milligrams starting amount because that doesn't matter. We want to know how long it gets to half of that. Well, it's just when this is at 0.5, we're at half of that amount. So you can construct a table. Time, 1, 2, 3, 4, 5, and on up. And then we're going to just do the factor here. Now, I'm not going to start out at 1. I'm going to probably skip up to like number 5. So let's do number 5. 0.87 to the power of 5. What does that give us? You get 0.498. Yeah, that's 0.498 is really close to 0.5. So I may have actually guessed it on the first try. But let's test the one right before this to see if it's closer. Why am I doing the one right before instead of the one right after? Well, 6 is going to be even smaller because we're decaying. This is a little less than 0.5, so let's make sure that the 4 hours is not closer to it. So 0.87 to the power of 4 is your 0.573. Yeah, so that's further away. So it looks like that 5 hours is about as close as we're going to get to a half-life. Because this is a little bit less than half already at 5 hours, we know that it actually did make it to half the amount a little bit before 5 hours. But 5 is close enough for what we can do right now. Then number 2 on that out of class exercises was talking about a 401k investment. So we were looking here at Joan had money in her 401k that she was looking to invest. We're using P for the amount of money in the plan. We're going to need to find a starting amount. What did they give for a starting amount here? Doesn't really give a starting amount, does it? It just says 6% increase. So I'm going to use P0 as the starting amount. Now for this one, she's gaining 6% per year. Would I put in 0.94 here to the power of t? Okay, so anyway, back to Joan. She's got 6% per year. So am I going to put 0.94 in here? Why would it not be 0.94 here? Perfect. This is increasing. 100 minus 6 would be 0.94. That would be decreasing. So we don't want the 0.94. What do we want in there? 106, right? 100 plus 6, which comes out to be 1.06 to the power of t. So t now is in years, because that is 6% per year. So they're asking us, we have our basic model there, depending on what the initial amount of money is. I guess they're saying to use P for the principal amount. They want A for the accumulated amount here. So they want to know what percent of the principal will Joan have after 32 years. So what we're going to do is we're going to just use this factor for 32 years. 1.06 to the power of 32 gives us what number? It's 6.453. So what that's telling us is after 32 years, what Joan has is 6.453 times as much money as what she started with. So 6.453 as a percent is 645.3% of the amount of money she started with. That's a pretty decent return. So then the next step, one of the next questions, I'm just kind of skimming some of the calculations off of the homework here. How long does it take to double? Well, again, we don't have the starting amount. Well, they give us the starting amount in part C, but we don't have to have the starting amount because that doesn't matter. The time it takes to double is just whenever this factor of 1.06 to the power of t equals what number? You had it? 2. When that equals 2, this is doubled. Because if you think about it, the amount of money in the account is equal to the principal times this factor, 1.06t. Well, the amount will be twice p when this equals 2. So you would make that table, again, of time and years and your factor amount here. 1, 2, 3, 4, 5, 6, 7, and so on. Let's try 5. 1.06 to the power of 5, what would that give us? I'm getting 1.338. Does that sound right? Okay, so that's way too small. So we're going to keep going here. Let's do like 8, 9. Let's try 10. See what you get when that is to the power of 10. .79, 1.791. So we still need to be bigger yet. So let's jump up to 15. What do we get? 2.397. So that's too far. So we know it's somewhere between 10 and 15 years. Let's try 13 and see what we come up with. So 2.13 we'll call it. Well then, that's still a little bit too long, too big. Let's jump back to 12 years and see what that gives us. $2.01. That's probably as close as we're going to get. So I'm thinking 12 years appears to be our time. Now remember we had mentioned yesterday the rule of 72 when it comes to compound interest. 72 divided by 6 is 12, so that makes sense. 12 years is a logical spot. So now here's the question. Without having to do any more examples on the table, how long would it take to quadruple? Quadruple means 4 times. If it doubles in 12 years, how long till it's quadruple the amount? Perfect. Yeah, let's just pick a number. Let's say we start out with $1,000. That's year 0. In year 12, that will have doubled to be $2,000. In year 24, that's 12 years from year 12. That 2,000 will have doubled to be 4,000. So that is quadruple the starting amount. Perfect. Okay, so just some things I wanted to point out in our homework. So remember that out of class exercises for M6 or for M5 is due tomorrow if you're still finishing those up. How many of you do submit those on the Quantway website? Okay, and the rest of you print them off and email them? Okay, you submit them too? Okay. The site wouldn't work or? Okay. The same answers, but they're telling you it's wrong? If that happens, just write down the answers that you have and send me an email with those answers, and I'll go through and compare them for you. Which problem are you working on? Okay. So M4 out of class. Let's take a look here. So 2 and 3 here. So number 2, the table below shows the salary for new employees. Is that the one? So a new employee earns $25,000 in base salary. Plus 8% commission after the first $2,000. So here, the way I would work on a model like this is I would write it out in words. So their pay is equal to, they get $25,000 no matter what. So that's their base pay. Plus their commission rate times their commissionable sales. Now, the reason I say commissionable sales instead of just commission sales, or instead of just sales, is because they don't get commission until after $2,000. So to fill out this model. Is this the right problem? Okay. You got the $25,000, their base, plus their commission rate is 8%. Commission sales is their sales minus 2,000. Okay. Yeah. Okay. So that's the thing, is having that minus 2,000 there. Okay. Then number 3 was. Okay. Let's take a look. So according to the article, major soft drink companies continue to battle. Another segment continues to grow. That segment is bottled water. 2010. Company sold 13.78 billion gallons of carbonated soft drink. So it's carbonated, and 8.74 billion of water. So 2014 then, carbonated sold as 12.75 billion, and water was up to 10.87 billion. And let's see here. What was the rate of change for the soft drink sales? Yeah, your rate of change, if you were graphing this, so if you're looking at rate of change, you got to look at the graph. On the graph, of course, this horizontal axis would be the year. So that'd be the 2010 and the 2014. And the vertical axis here would be your sales. And for carbonated, that went from 13.78 down to 12.75. Which probably makes it a little less drastic. So what we have is we have a drop. This is our difference in that vertical variable, 13.78 minus 12.75. Our difference in years is just 4 years. Now you have to be careful. You subtract this, you get 1.03 over 4. That is a negative 1.03 because it went down. Technically, I probably should have done 12.75 minus 13.78 because 12.75 was the ending value and 13.78 was the beginning value. But it is a negative 1.03 change divided by 4, which is a negative 0.2575 per year. Now that's in billions of gallons per year. Would be that rate of change. Does that make more sense? Okay. Okay. Write the linear model. Okay, so we're assuming that it was a constant linear rate for the carbonated beverages. The amount, and I'm just going to use Y. What was the starting amount in 2010? The 13.78. The rate of change was minus 0.2575 times X. I might be slightly off on this calculation. I'm not totally sure if that's right. It is right? Okay. And then the same for water. You've got a starting value of, for water, it was 8.74. That's increasing, so it's going to be plus whatever its rate of change is times X. So now, what'd you get for a rate of change on the water? 0.5325. Okay, now the big question is part C of that question 3. What year would you expect them to be equal? Well, I would just take this, when they're equal, this y equals that y, right? So I would just take this expression and this expression and set them equal. So the 13.78 minus 0.2575x has to equal 8.74 plus 0.5325x. And then you can solve that for x. And that tells you, remember, x is years after 2010. So whatever x comes out to be, you're going to add that to 2010 to get what year they're equal. Any other questions? Okay, yes, so that out of class exercises 4 and PNL 5 were due yesterday. If you need more time, let me know. Or if you have them printed off and you need to, oops, there, I'll try to get my mic better. So yeah, if you need more time on those, let me know and I'll reopen them for you. Or if you have them printed off and you just want to email them to me, I'll still accept those for you. That'll be fine. If you'll notice, by the way, if you go on Blackboard, I started the grade book in Blackboard, and what I did was I did for Unit N, I entered in a homework grade for what I had for homework, and that was out of two. What I did is I added up all the points, and I kind of crunched it into 200 points. So I added up all your points, I got a percent, and I just doubled that percent to make it 200 points. For the assignments that I have from you, those of you that have submitted them in Quantway, I did go through. You said there were some that had to be graded manually yet. I did go through and grade those. I didn't change the grade in Quantway because I'm still learning the software yet, but I did add up those points so that the total that is in Blackboard should reflect those points from having to go through and manually grade those. All right, that's just our New Richmond connection going down because there's nobody there. Anyway, so that would be your homework grade is out of 200 points. There's a class participation for doing the class activities. Because I don't have any attendance records, I just gave everybody the 100 points for class participation for Unit N. And then there's a test out of 100 points. So that's how your grade is breaking down so far for Unit N. 400 points, half of it is the homework, 1/4 of it is the class participation, and 1/4 of it is the test. And that's how I'm going to do the other 2 units as well. If you look at it, there's a couple of you that I just didn't have all the assignments for Unit N. So if you're getting a couple of you sitting around 80 or 90 points out of the 200 for Unit N for homework, that just means I don't have them. If you have them somewhere and you can resend them to me, that would be wonderful. I'll make sure I regrade those and put them in for you. If not, we'll figure something out for you so that you're not hurt by things being lost in our transition here. So just so you're aware of how your grade sits, you can check that on Blackboard now, on the Nicolet College Blackboard. Okay, so on with our new material. So the preparing for next lesson that you guys did for M6 here, we're looking at solving equations. And we're looking at basically inverse operations. All of our operations in math come in pairs, and those pairs are called inverses. The first pair of operations we usually encounter is addition and subtraction. And they're inverses because to get rid of one, you use the other. For example, somebody give me a random number between 10 and 20. Just throw one out. 14, good. Somebody give me, if my pen will work here. Somebody give me another number between 5 and 10. 6. So if I take 14 and I add 6 to it, what do I get? 20. If I want to turn that 20 back into a 14, what do I have to do? We subtract the 6, right? So adding 6 and subtracting 6 are the opposite of each other. They reverse each other. They undo each other. The same happens with our multiplication and division. So let's start out with that same 14 again. Only we're going to do 14 times 6 this time, which is 84. If I wanted to turn that 84 back into 14, what do I have to do? Divide by 6, yes. So multiplying by 6 and dividing by 6 are again inverses. One of them reverses or undoes the other. All of our operations come in these pairs, and there are more pairs than what you might think. Like if I have 5 to the power of, let's keep it a little bit more simple than that. 5 to the power of 2 is what? 25. If I want to get back to 5, what do I do? Square root. There we go. Square root of 25 takes us back to 5. Yeah. Well, when you're dealing with just squared, it's easy to think of, like you said, just dividing by the 5. If I have 7 to the power of 3, that gives me 243. If I want to take that 243 back to a 7, we have cubed roots that do that. Notice the correlation, power of 3, it's an index of 3 on our root. The square root, even though there isn't an index written there, it's implied that that is a 2. You know, we might have 2 to the power of 4. Well, 2 to the power of 4 is 16. What do I do to the 16 to turn it back into a 2? It's actually going to be a 4th root, right? Because this is a power of 4. I know what you meant. So it's a 4th root. So the power of 4 is undone by a 4th root. Well, these are all important tools. The inverse is very important to us for solving equations. When we look at equations, and I know you guys have all solved equations before, let's just kind of briefly go back through the process. If we start with x equals 7, technically all equations start out in this form as a variable equals a number or a number equals a variable. And they are built from there. So our basic operations can be used to build onto this equation. For example, we might add 2 to the x. That becomes x plus 2. However, equations are balanced scales pretty much. Whatever's on one side exactly balances what's on the other side. So if we add 2 to the left side, to keep that balanced, we have to do the exact same thing to the other side. We add 2, 7 plus 2 is 9. So we have now built onto this scale and made it more, or onto this equation and made it more complex. If we're asked to solve it, what we're being asked to do is take it back apart. Well, to take it apart, we would do the opposite. We built it by adding 2. The opposite would be subtracting 2. Very good. That gets rid of this 2. 9 minus 2 is 7. That takes us back to that basic form of a variable equals a number. So solving equations is nothing more than trying to look at it and figure out how it was built and then take it apart. For example, we have 3x minus 7 equals, well, let's just go with 20. If I want to look at how this equation was built, to do that, I ask what has been done to my variable, what's been done to x. So I'm looking at just this side of the equation over here with the variable on it. If I'm thinking of order of operations, if x were a number, what would be the first thing that we would have to do? Would we multiply it by 3 or would we subtract 7? Order of operations says that first we would multiply by 3. Well, I'm not talking about solving it yet. I'm talking about how this was put together and built. You are right on solving it. So if x was a number, the first thing that would happen to it would be multiplied by 3, and then the 7 would be subtracted from it. Now, when we're asked to solve the equation, we're being asked to take it back apart. Now, if you think of maybe you put together a piece of furniture that you've bought, or you put together a toy for a kid, if you've just finished, you've just put on the last piece and you've finished. If you needed to take it apart, what was going to be the first piece you take off? The last piece you put on, exactly. So when we're solving an equation, we are just taking it apart. And to take it apart, we start off by taking the last piece that was put on. The subtracting 7 is the last piece that is put on. That's the first piece we're going to remove. And of course, to remove that, what's that? Yeah, the reverse order of operations, yep. So to remove subtracting 7, how do we reverse that or undo it? We add 7. That makes that go away. And yes, we do it to both sides so that stays balanced. So 3x equals 27. And then, of course, the next step, we would divide by 3. That's undoing the multiplying by 3. So x equals 9. Well, our equations could get a little more complex than that. We might have x to the 4th minus 7 equals 74. So if I look at how this was built, what was done to x to build this equation? The power of 4, yep. And then Then 7 was subtracted from it. Good. To take it apart, we're going to take off the last piece that was put on first, which is subtracting 7. We'll do that by adding 7. So x to the 4th equals 81. Now the reverse of taking a power of 4 is, the 4th root of 81. Now on your calculator, the 4th root can be done a couple of different ways. You'll see there's the square root key is usually above your x squared key on your calculator, depending on what type of calculator you have. My power key is this caret key here. That's the key that would take things to the power. Most of you either have a caret key like that. It looks like it's called a caret. It looks something like that. Most of you above that key would have either an x root or an n root as the second function. And the way that would work is you would enter the index of the root, that's this number up here, you would have to hit second or shift and then press that key and then enter the number. So you'd have to do 4, second, and then that caret key with the X root. But the second is saying we're using the X root rather than the caret, then type in the 81. So I'm going to have you see if you can get that to calculate out for you. The 4th root of 81. That is perfect. If you get that answer and you're not sure of it, you can always double check it. Is 3 to the power of 4, and make sure that gives you 81, and it does. So what we ran into then in the last class, and it was part of your preparing for next lesson stuff, is we have something like 5 to the power of x equals 25. Well, what does x have to be here? 2, there we go. 5 to the power of 2 equals 25. So we know x equals 2. Or we might have, come on, 2 to the power of x equals 16. What does x have to be? This will take a little longer. 4, very good. 2 to the power of 4 equals 16. Well, how can we solve this without having to just guess and check? Well, there is an inverse. When we have a number, like let's just use 10 to the power of x, the inverse of going to the power of x is a logarithm. So what the logarithm is, and we call it log of a number, let's say the log of 100. You guys have your calculators out. Can you find the log key? And just do log of 100 and see what it gives. Should be 2, exactly. What the log key is saying is, log of 100 is saying 10 to what power equals 100. So it's finding that x has to be 2. The log key that's on your calculator is implied to be base 10. This base is telling us what number is the base of the exponent. Remember that exponent has 2 pieces, a base and a power. So just like with our roots and powers, if we had x to the power of 5, we had to use a 5th root to reverse that. The same is true for these exponentials that we have. 10 to the power of x, since 10 is the base, we have to use a log with a base 10. Now, unfortunately, your calculator only has 2 different log bases that it uses. The standard log key is base 10. That would solve anything that's 10 to the power of x. There's another key on your calculator that's ln key. The ln key is base, and we haven't talked about the letter E yet. E is kind of like pi for circles. It's a natural constant, 2.726 or 2.729 and blah, blah, blah. It keeps going on. That one's going to become more important. I'm not even sure if we're going to see that one in this course because I haven't looked that far ahead yet. But it's just another way of doing it. E appears enough in nature. If we're looking at continuously compounded interest, growth and decay of currents and charges in electrical circuits goes off of that constant. So because E is used enough in nature, we developed a special log for it. So what we're going to be working with is that log key, which is base 10. So if we have something that is 10 to the power of x equals 100,000. Since the base of the exponent is 10, we can solve this with the log key. If I take the log of both sides, log of 10 to the x, it's the log and the 10 to the power of cancel each other out. That's just x. So then log of 100,000 on your calculator is going to give you what's your calculator spit out for that one? Log of 100,000 should be 5, I believe. Perfect. So that's kind of the gist of that stuff in the preparing for the next lesson. So what I want you guys to work on here for just a little while, we're in M6 now. We've talked about these a little bit. I want you to take a few minutes, work on problem number 1 and problem number 2. So problem number 1 is just your basic add, subtract, multiply, and divide to solve an equation. Problem number 2 is using powers, and then of course having to use roots to reverse them. So I'm going to give you guys about 4 or 5 minutes to do those problems quick, and then we'll talk about them. So let's take a look at how these worked out for you. In number 1, we had x plus 5.4 equals 11.6. What do you have to do to solve that? Perfect. You subtract the 5.4 and you get x equals, careful, 11.6 minus 5.4. 6.2, there you go. Then the second one, t minus 28 equals 44. What do we have to do to solve that one? Add 28, good. So t equals 72, perfect. And then the next one is 5w equals 38. What do we have to do to solve that one? Divide by 5, w equals 7.6 is perfect. And then the last one for number 1, we have d over 12 equals 3.5. What do we do to solve that? Multiply by 12, we get d equals 42. Good. So all it was looking at the equation, seeing what operation had been done to the variable, and then doing the inverse. Now for number 2, it might have been a little trickier because we have powers. So the first one for number 2 is x squared equals 36. What did we do to solve that? Square root, right? Yeah, the square root of 36 is 6. Now, if the purpose of this lesson was to talk about roots, technically that's 6 or a negative 6, because negative 6 squared also equals 36, but we're not going to worry about that technically. Go ahead. Yep, if you had like something like this, x plus 2 squared equals 36, you would square root this. So you've got x plus 2 equals, because the square root and the squared cancel each other out, The square root of 36 would either be 6 or negative 6. Then you'd have to solve both of those equations. You'd subtract. Okay. Well, if there's extra steps, you really should do it that way. Yes. Like here, you'd subtract 2 in both cases. Here, x equals 4. Here, x equals negative 8. Since there's nothing extra to do here, once you square root, it's just either x equals 6 or negative 6 are the two possible answers. Realistically, I'm happy with the 6 for now. Yep. Oh, gotcha. Like this? Sure. Well, so what we're going to need for this next example, we got t to the third equals 27. The square root only works on a power of 2, on squared. So to do the power of 3, we have to use a third root. So the third root and the power of 3 cancel out. That would be t. So the third root of 27, what that is asking is, what number to the power of 3 equals 27? Do you have your calculator with you? Okay, what kind of calculator do you have? What model? Okay. Sure. What? Okay. Most phones do roots a little bit weird. You have like a Y root like that. That's the button you most likely want. Depending on your phone, to do a third root of 27 like this, you should type in. Yep. Yeah, you can just type in the 27 and use the third root key. That'll work. That should give you a 3, right? Perfect. What if you have x to the power of 5 equals 3,125? So we have to use a fifth root, right? So for your phone, what you would have to do the fifth root of 3,125, there's going to be one of two ways depending on what app is on your phone. Yes, it is. So did you do 5, then that key, and then the 3125? Okay, perfect. So that works great. As long as you've got that figured out, that's exactly what you need to be able to do. Yep. Anybody else have questions on how to calculate that fifth root? So that does come out to be x equals 5. Now again, if our purpose was to talk more about roots, we would look at, okay, odd roots only have one answer. Even roots could either be positive or negative. But like I said, we're not going to get, that's not really the purpose of where we're going today. So then all we have to do is reverse that. We're figuring out what number. And of course, to double check these, x to the fifth equals 3,125. We got that answer of x equals 5. To double check that, we could just put that 5 back in for x. So 5 to the power of 5, and on your calculator, you'd punch that in, and it does give you 3,125. So we get that same result on both sides. So now what we're looking at is what happens if we have 5 to the power of x equals 25. What number has to go in there for 5, or for x? 2? Yes. 5 to the power of 2 is 25. Very good. The second one is asking 3 to the power of x equals 81. What has to go in there for x? Careful. You may have to make a table. You may have to make a table. Obviously, it's not going to be 1, but they do 2, 3, 4, 5, 6. So if x is 2, this is 3 to the power of 2, which would be 9, right? If x is 3, it would be 3 to the power of 3, which would be 27. There you go. If x is 4, 3 to the power of 4 would be, careful, 81. So that's what we need. You did 2 to the power of 4, didn't you? Yep. So that's what we need is the 4. So that's x equals 4, because if I put 4 in here for x, it gives us the same value on both sides of the equation. So I want you to try, I did the 2 examples in the packet, but I want you to try this. 5 to the power of x equals 625, find x. And 2 to the power of x equals 512, find x. So I want you guys just kind of work out, see what you come up with for x for those 2 equations. And what we're going to do is it's 11:30, so let's take 11:33. Let's take a few minute break as well. So what I'll do is we'll talk about these at 11:40. So if you need to take a short break, go ahead and do that and then work on these and we'll talk about them at 11:40. So for 5x, or 5 to the power of x equals 625, we needed to find a number that we could put in there for x so that 5 to that power equals 625. What'd you come up with? Well, we know it's bigger than 2 because 5 squared is 25. So we'd start with 3, 4, 5, and try them until one works. What number worked? Yes, 5 to the power of 4 equals 625. So 2 to the x equals 512. So 2 to what power is 512? Now remember when we did the examples, this is the reason I did some of the homework from the M5. Remember I started out, I didn't necessarily do one, start out at 1 and work my way up. I made my table, but I might have started out at like 3 just to see. Well, at 3, 2 to the power of 3 is 8. That's way too small. If we jump up, well, let's see, we see 7 there, 2 to the power of 7. Well, 2 to the power of 7 is, what, 128? That's still too small. Which one did it end up being? X equals 9. 2 to the power of 9 is 512. So again, all we could do on these was try numbers, take a guess, an educated guess, and try them and see what works. Basically, using a table like this is one way to organize it. There are other strategies that could work. We want a way to calculate it directly. Now, as we mentioned from the preparing for next lesson, the opposite of a power of x, 10, oops, my pen has stopped on me again. There we go. 10 to the power of x. The inverse of that is a log. And that log, of course, is base 10. We don't write it in there. If the base is not written in there, it's implied to be base 10. So when you see log, that little 10 is implied. If we are told that 10 to the x equals 20,000, It's asking us 10 to what power is 20,000? So the way we would solve that, just like we use a square root to get rid of x squared or a fourth root to get rid of x to the fourth, we have to do the log of both sides. So the log of 10 to the x, the log and the 10 to the x cancel out, giving us x. Log of 20,000 gives us what? 4.301 about? Oops, gotta get rid of that. Did everybody find their log key on their calculator? Okay. So that does work out. Log of 20,000 is 4.301. This only works, again, if the base of that exponent is a 10. So the next section here, problem number 4, gives you two equations where it is 10 to the x equals 135 and 10 to the x equals 12.2. So I want you guys to take about 2 minutes and calculate those out and see what you come up with for those values. Yes. So 10 to the x equals 135. What did we do to solve that? You bet. We did log of each side. Of course, that cancels out the 10. X equals, what's the log of 135? 2.130. Perfect. How did I know that it was a 2 before you even started to answer, by the way? Perfect. Perfect. Yeah, 10 squared is 100. 10 to the third power is 1,000, right? So I know that 135 is between 100 and 1,000. So it's between 10 squared and 10 to the third. Perfect. Good thinking. So then we had the 10 to the x equals 12.2. Now, without punching this in, if we thought about it, 12 is between 10 and 100, correct? So 10 to the power of 1 is 10. 10 to the power of 2 is 100. So when I do the log, it better be between 1 and 2. So if we do the log, what do we get? .086 sounds correct. Now we can double check these. If we put 10 to the power of 1.086 and see what we get. Now it may not be exactly 12.2 because these are rounded off. But 10 to the power of 1.086 is 12.1898. That's close enough to 12.2. That's just round off error is all that is. Go for it. That's a very good question. There's two cases here. Remember, the exponents have two parts. Let's say I'm just going to do 10 to the power of 3. 10 is the base. 3 is the power. When the variable x is the base, so that would be like x to the power of 5 equals 32. The variable you can see is in the base of the exponent. That's where you're going to use a root. So that's the power of 5. We're going to use what kind of root? Fifth root. Perfect. Because the index of the root has to equal the power that we're trying to get rid of, the exponent. So that gives us x equals 2 there. If the variable is the power, like 5 to the power of x equals 625, that variable is the power now. That's where we're going to use the log. Now, we don't know how to do a log base 5 right now, so I can't, that's kind of a poor example. All we know so far is if it's 10 to the power of x, we can solve it. If it was 10 to the power of x equals 625, we could just do a log of both sides. The log and the 10 to the power of cancel out. Log of 625 is going to be 2 point what? Perfect. So the question is, how would we solve something like this that is 5 to the power of x instead of 10 to the power of x? Well, when we deal with logarithms, if the base is not 10, so we have a base other than 10, we can use a change of base formula. I'm not one that likes to usually throw out formulas and tell you to memorize them, but this is one of them. So if I have a log base something other than 10, so I do log base A of B. I'm going to stay consistent with the notation in the book here. To calculate that, I can use a log base 10 of B divided by the log base 10 of A. So let's take a look at this. Log base 2 of 8. Now remember what this is asking, log base 2 of 8. It is asking is 2 to what power equals 8? Well, we know 2 to the third power equals 8, correct? So we know this has to be 3. But to use the log buttons on our calculator to do it, it's going to be log of 8, the number here, divided by log of the base, which is the 2, log of 2. So if we type in log of 8, make sure I close my parentheses, divided by log of 2, we should get 3. And we do. So what this is telling us is if we have like 5 to the power of x equals 625, to solve this, what I really need to do, what's the base of my exponent here? 5. So to solve this, I really need a log base 5. Since our calculator does not have a log base 5 button on it, we have to use that change of base. So over here, the log 5 and the 5 are going to cancel out to give us x. Log base 5 of 625 is going to be found by doing log of, what number is going to go on top here? The 625, exactly. Over log of what the base would be is 5. So log of 625, make sure you close the parentheses, divided by log of 5 is 4. If you double check that, by the way, 5 to the power of 4 is 625. We found that answer earlier. So how would we do, let's say I have 8 to the power of x equals 4,096. How am I going to solve this? Well, first of all, do I need a root or a log? The variable is the power, so we need to use a log. What base of a log do we need to use? Well, what's the base of our exponent? 8. So we need log base 8. So again, the log base 8 would cancel out the base of 8 in my exponent, giving me x equals, this is log 8 of 4,096. So we have to use that change of base formula. So we've got log over log, what number goes on top? 4,096, and on bottom will be log of 8. So if you divide that out, what are you going to get? Fours, perfect. Anybody having problems getting that to work on their calculator? Okay, so what if I give you something a little uglier? 1.2 to the power of x is equals 1.728. I want you guys to take a little bit of time and just think about that. We'll talk about it in about 30 seconds. Think about what you would do to solve that. Try it in your notes. So we're going to have to do a log or a root. Which one? It's going to be a log because the variable is in the power, so it's going to be a log. And a log of what base? What's the base of our log going to be? 1.2, very good. So the log base 1.2 and the 1.2 in the base of our exponent cancel out. So now we've got to do log base 1.2 of 1.728. So that change of base formula, log of what number goes on top? 1.728, good. And on bottom? Log of 1.2, and figure that out. That calculates out to be what? Three, perfect. Now I purposely made those examples come out to be a whole number answer. They're not always going to be that way, but it looks like they do a very good job of telling you what to round to. So I want you guys to try now number 5 in M6 here. Solve those 3 equations and use this change of base formula for the logs to solve for x. I'll give you a couple minutes and we'll go over those. So let's take a look at these. The first one, 3 to the power of x equals 27. What did you get there? 3, perfect. X equals 3. That would just be log of 27 divided by log of 3 should give you 3. For the second one, 6 to the power of t equals 200. So let's start out, what formula did you use? What logs did you use to solve that? Perfect. Log of 200 divided by log of 6, which gives you? Perfect, 2.957 to the 3 decimal places. Any questions on that one? Okay, and our last one, 1.032 to the power of t equals 2. First of all, what logs did we use here? Careful. The other way around. Log of 2 over, because remember, the base of our exponent here is the 1.032. So that has to be the base of our log. So log base 1.032 of that. So the 2 goes on top. So what do you get there then if you do it that way? 22.006. Does that look right? Okay, you've got it? Oh, sure. Any questions? Is it clearer now or? Okay, perfect. Now this number right here might look familiar to you from Monday. We've talked about a lot since then. That 1.032 comes from a 3.2% increase. So what we're looking at now is we're looking at number 6 in your M6 is taking us back to a problem we looked at last class where we had the university had a tuition starting out at $16,500 and it increased by 3.2% every year. So it was $16,500 in 1977 and increased by 3.2% each year. And we came up with a model for that. The model was the amount of tuition was equal to that starting amount, 16,500, times, they're using parentheses, so I'll use parentheses, 1.032 to the power of t, where t is in years after 1977. Now, first, where did the 1.032 come from? Oops. Exactly. That is the 3.2% increase. It's 100% plus 3.2%. So it's 103.2%. So that is our exponential model for that 3.2% growth. Now, we had asked a question at some point. I'm going to stick an extra question in here that's not in the packet. We asked, how long does it take to double? And the reason I'm asking this is because it's really ties into this last equation we solved right here. What's double of 16,500? There you go, 33,000. So we're asking is we're solving for t here when or solving for the time when the tuition is 33,000. So we're solving for little t when big T is 33,000. So to solve this, we have to get the variable by itself. Now we've solved equations where it was just this piece. We haven't solved equations when there's other stuff. But what we have to do is we have to get this piece by itself. Right now, what's keeping it from being by itself is the 16,500. What operation is attaching it? What operation goes right here? That's multiplication, right? So how do we reverse that? How do we get rid of that? We divide. Good. So we're going to get rid of the 16,500 by dividing by it. Since it multiplies the 1.032 to the power of t, we're going to divide by it. And you'll notice what we get over here is just 2. So 2 equals 1.032 to the power of t. If we look back about 5 minutes ago, 8 minutes ago, we just solved that equation. Since our variable is the power of our exponent, we're going to solve it with a log, and our log has to have the base of 1.032. So that cancels out here, giving us t, and we saw that the log of 1.032, of 2, we did, oops, sorry, my controls are going wacky on me. That was going to be the log of 2 over the log of 1.032, which gave us a result of 22.005, right? 006, apparently. So now, rather than having to fill out those tables and guess numbers and check them, we can now solve these equations directly. So I want you to do is solve this. How many years after 1977 did the tuition reach $42,000? So remember, our base equation is the tuition, capital T, is 16,500 times 1.032 to the power of little t. So I'm going to give you about 2 minutes to try to solve that, then we'll talk about it. So where did we put the 42,000? You put it in for A. 42,000 equals 16,500. Then what do we do to solve it? Oops, you have a question. Perfect. Did you have a question, Sam? Or? No. Okay. So yes, we do divide by the 16,500. So now I'm going to show you a little trick here. We're going to keep this in our calculator. I would do 42,000 divided by 16,500. And I get that answer. If I write it down and try to type it back in, it's going to be rounded. So I'm just going to leave that on my screen. I'm not going to hit clear. I do have to write down a number here, though. I'm just going to write down 2.54 equals the 1.032 to the power of t. So now, of course, I'm going to finish this off by doing what? Perfect. I have to do a log base 1.032, and because my calculator doesn't have a log.base, I have to do the log of 2.54 repeating over the log of 1.032. So on my calculator, what I'm going to do is this. I'm going to do log, and then so I don't have to type that back in. Most calculators have an answer key. So I'm going to do second answer to have the calculator pull in that answer, divided by log of 1.032, and I get 29.66. So that's 29.66 years after 1977. So now I have to be careful. If it's asking what year does this happen, I have to take my 1977 and I have to add 29.66 years to it. So that's going to be, what, 2006.66. So that's telling us somewhere between 2006 and 2007 is when the tuition hit 42,000. So this process can be applied to any of these exponential problems to solve it. On the next piece here, problem number 8, they give us an example for compound interest. They give us the formula, I should say, for compound interest. Compound interest is for savings accounts where the interest is added in every set period. N is the number of periods in a year. So if I have a bank account that's compounded monthly, that's telling me that N equals what? If it's compounded monthly, how many periods are there in a year? 12. Very good. If it is compounded quarterly, that's telling me N equals what? 4. There's 4 periods in a year. So N is 4. So the formula they give us there is the amount in the account, the balance in the account is equal to the principal, the starting amount, times 1 plus R over N to the power of NT. Now the 1 here just represents that 100%. R is our percent increase, our rate of increase. So an example we could use is, let's say Pat invests $8,000 at 5% interest, compounded quarterly for 7 years. So in this formula here, we're going to be looking for the amount P, the principal or the starting amount, is the $8,000. 1 is a constant. What is R? What's my rate? 5%. We're going to have to write that as a decimal. So 0.05. That's going to be divided by, what's N here? It's compounded quarterly. So N is 4. Good. And then we're going to go to the power of N times T. Well, N is still 4. T is the number of years, which is 7. If I look at this, n times t, 4 times 7 is 28. There's 28 quarters in this investment, is what that's telling me. I don't know why I wrote n down here when I said 4. That should be 4 over 4. So to punch this in our calculator, 8,000 times parentheses, 1 plus 0.05 divided by 4 to the power of, I'm going to cheat, just type in 28, we get that balance. We're running out of time here, so for next week, I want you to work on PNL M7 and out of class exercises for M6. That finishes up, basically M6 is finished up with this example. There's a couple other little things that you should read through just to see how these logarithms apply. They're basically what we're doing is going over all those examples, the exponential models we created last class, and applying the logarithms to solve them. So this will be due on Tuesday of next week. We'll go over any questions on them next Monday. And like I said, if you have any assignments, if you look at Blackboard, look at your grade, if there are any of the Unit N homework assignments that you still have that you may have scanned and submitted that way, if you still have them, please scan them and submit them to me, and we'll make sure your grade's straightened out. Okay, you guys have a great day, and we'll see you on Monday.